So hydrostatic lubrication. This is what a typical diagram of hydrostatic lubrication. Okay, this is a runner, and this is a W means it's a load which is applied on the hydrostatic bearing, and this one is called as a step. Okay, and here Pi means inlet pressure. Pi means inlet pressure from the external source, means it is connected to the pump. So it is connected to the pump. So the pressure which is at the pump is called inlet pressure, which is denoted by Pi, and P naught means it is external pressure, means atmospheric pressure, and H naught, this is the H naught distance. H naught means a fluid film thickness. H naught means a fluid film thickness or thickness of the fluid film. Ri, it's a inside radius of the shaft. This Ri is a inside radius of the shaft. This is a shaft. Okay, this radius is Ri, and R naught outside radius of the shaft. This is another shaft. Okay, so this R naught is a outside radius of the shaft, inside and outside. W is the radial load acting on the journal bearing, and B is the width of the surface or bearing. So this is the width of the surface of the bearing. Whatever the fluid film is there, okay, actually it is in the circular. Okay, actually it is in circular. When it is unwrapped, okay, it is become a straight. So that width is called as this B. So how you are going to measure this width or this length? Actually it is circular, correct? The thickness which is present between the two surfaces, it is in circular, because these two are also circular. So the fluid film is also a circular, but we are making it straight or unwrapped. It is actually curved. When it is unwrapped, it is become a straight. Then how you are going to measure that length, that width or whatever the length? How? Not in terms of diameter. It is in terms of circumference. Okay. Just take an example of one thread. When the thread is circular, okay, the thread is in circular, make it circular, and after circular, when you make unwrap means when straight, okay. So how you are going to measure that? So one thread, actually it's circular. After it is making straight, then it is become circumference, no? Okay, that length is nothing but circumference. That B is called as circumference. That circumference is nothing but a 2 pi r. Circumference of a circle is what? 2 pi r. Circumference of a circle is 2 pi r. Clear? Okay, that is a width B. The B value is 2 pi r. The same fluid film, okay, here it is in circular actually, but when we unwrap this, it is become a straight, and that width is 2 pi r. And L is the length of the bearing. That is what the length of the bearing. This is dr. For a small body, we consider this is dr. That is what? L. Clear? And this is a front view of a hydrostatic bearing, and this is the front view ಆದರೆ ಇದು ಯಾವುದು? Yes, it is a top view. If you see from the top, everything looks like a circular, okay. So first inside, outside, and this is what the small a prismatic element we are considering for derivation. For our derivation, we are considering this small prismatic imaginary circular element for derivation. See, in the Reynolds equation, we consider a small cubical element, correct? Consider Reynolds equation and we are applying the boundary conditions. It become a for an entire thing. Here also same thing. First, we are considering for a small element, and after applying the boundary conditions from minimum to maximum, we will get the entire. Clear? For the derivation purpose, we are considering a small element. See, this is a small element. Okay, it is also circular. The same circular we are considering for derivation, and here it is become a straight, a circular just like a thread. Okay, and once it is unwrapped, it is become a straight. And along this element, this is what the pressure distribution. Clear? This is a pressure distribution. The pressure is maximum. When the pressure is maximum at inlet, when the fluid is enter, pressure is maximum, and the pressure is minimum, yes, at the outlet. When the outlet pressure is minimum P naught, when the inlet pressure is maximum. ಅರ್ಥ ಆಗ್ತಿದೆಯಾ? ಸೊ ಪ್ರೆಷರ್ ಇಲ್ಲಿ ನಿಮಗೆ ಮ್ಯಾಕ್ಸಿಮಮ್ ಇರುತ್ತೆ ಇನ್ಲೆಟ್ ಅಲ್ಲಿ, ಅಂಡ್ ಔಟ್ಲೆಟ್ ಅಲ್ಲಿ ಮಿನಿಮಮ್ ಇರುತ್ತೆ. ಕ್ಲಿಯರ್? And for this imaginary element, the pressure is P. We don't know what is that, but we name it as a P. ಇಲ್ಲಿ ಕಾಣುತ್ತಲ್ಲ, this is a pressure at imaginary element. This is a pressure at inlet, and this is a pressure at outlet. Maximum, minimum. But in between maximum and minimum, there is an imaginary element. It is having pressure P. Clear? Notations artha aita? So next, this is same as a flow between parallel plates. This is same as a flow between parallel plates. See, these are the two parallel plates. Okay, these are the two parallel plates. So this consider as a flow between parallel plates. It is similar as flow between parallel plates. Okay, so here we directly consider equation is a flow in the parallel plate equation. We already derived flow in the capillary tube, flow in the parallel plate in the first module. The first module we already derived the two equations. What is the flow in the parallel plate? What is the flow in the parallel and capillary tube or circular tube? Okay, so here it yavudak match agutte. So it is suitable with two plates, correct? This is a one plate, this is another plate. The flow is between two parallel plates. Here there is no circular capillary tube ideyalle. If there is a any tube, then it is a flow in the capillary tube. But here there is a two plates, that's why we have to consider equation. This equation is called a flow in the parallel plates. You just take the help of data handbook. This is a data handbook. First equation, see here, eigenpoisson law, flow in the capillary tube, but namige enidu flow in parallel plates. Ya equation tagontira? Ellide flow in parallel plates. Flow in the parallel plates, yes, flow between parallel plates. Q idya? So flow between parallel plates, first one is the velocity. Okay, you don't take velocity here, we need a flow. So eighth equation, il kantidiya, rate of flow between the two parallel stationary plate. Q is equal to 2 TQ by 3 by, okay, so idanara consider ಮಾಡಬಹುದು, or else in terms of B and H. What I derived, okay, yes, B H cube. That H is replaced by T or thickness. Around the equation only they consider T, in some equations they consider H. Okay, here we taken H, B H cube by 12 mu dP by dx. This is the equation 1. We can call it as a flow in ಯಾವುದದು parallel plates. ಇಲ್ಲಿ ನೀವು equation ನ ನೆನಪಿಟ್ಕೊಳ್ಳೋ ಅವಶ್ಯಕತೆ ಇಲ್ಲ. It is already available in data and book. You just write the figure and explain the notations. Directly take the equation because it is matches with the flow between the parallel plate. So we consider a equation for Q is equal to BH cube by 12 mu dP by dx. That is called as a equation 1. Okay. So now you have to replace the values of B and H. Okay. Because the B value is, we already know that, width of the imaginary element. What is the width of the imaginary element? B is equal to 2 pi r. Correct? B is equal to 2 pi r. That you have to write B is equal to, here B is equal to 2 pi r, and dP, change in the pressure, same thing. It won't change in the pressure. Okay. But dx means, instead of dx, we consider the width of the length of the imaginary element is L. That is nothing but a dr. Previously, see this dr, or it is also called as L. Same thing we consider here. Okay. So now dP by dx we can replace by minus dP by dr. Now the value of dP by dx is replaced by dP by dr because it is in terms of r. That's why it should be dr, not in terms of x. Then what is the indication of this negative? Here dP by dx is positive, but I written dP by dx which is equal to minus dP by dr. Minus. Why? Yes, that is what. See, the pressure is decreasing. See, this is a inner radius. Okay, there are two radius, inner radius and outer radius. So inner radius pressure is maximum. Correct? Inner radius pressure is maximum because it is a inlet pressure which is directly connected to the inlet. So pressure is maximum. When the radius increases, what happens to the pressure? When the radius increases, pressure gradually decreases. So this is a minimum pressure. Pressure is decreases when the radius increases from R0 to Ri. So Ri to R0, inside to outside. Correct? So when R increases, pressure decreases. That indicates by this negative sign. So negative sign indicates that pressure decreases when R increases. That's why I have to write negative sign. And next H. So this H is there. But here film thickness, we can call it as a H is equal to, H is equal to H naught. H naught ಅಂತ ತಗೊಂಡಿಲ್ವಾ? See here. ಏನಿದೆ? H naught is a fluid film thickness. So H is equal to H naught. You have to replace that value. Clear? So now substitute all the values in the equation 1. Now substitute all these values in the above equation, and we can rewrite in terms of H naught, in terms of 2 pi r, okay, in terms of minus dP by dr, which is become, so 2 pi r H naught cube 12 mu minus dP by dr. Okay, I just replace that value in equation 1, and after that I just simplify. Okay, means this 2 get cancelled, it is become a 6. So 5 r H cube by 6 mu dP by dr minus this, we can call it as a equation 2. Okay, and here I want P because I want pressure. Okay, so separate P dP value. I want to separate this dP. Okay, and shift all these value to the left side. So now it is become dp is a separate term which is equal to, okay, dr minus ಈ 6 mu ಇಲ್ಲಿ ಏನಾಗುತ್ತೆ, ಇದು ಶಿಫ್ಟ್ ಮಾಡಿದ್ರೆ denominator ಬರುತ್ತೆ. It is in numerator, it will shift it to denominator. Okay, minus 6 mu q divided by pi r h naught q. Clear? So now you can call it as this. This 6 is constant value. So in this equation, I have to separate the constant values because it is easy for integration. Only integratable term is one side and constant term is another side. Because integration of constant term is become constant. Okay. So 6 is a constant value. Viscosity is a constant. Correct. Viscosity is a constant. 6 value is a constant. Q, flow rate is also constant. Here we consider the flow rate is constant, and pi is also constant value, and film thickness is also constant. It won't change. So these are the constant terms. So that make it separate. Okay. So make it separate. And here dr by r. So r is changes because radius is changes from inside to outside. It's the changing value. Okay. So dr by r. Now we can call it as equation 3. So apply integration for this equation. Yes. Integrate equation 3. Okay. Integrate equation 3. We get integration of dp is p. Okay. So integration of dx is x. Similarly, integration of dp means p. Okay. So differentiation of p means dp. It is reverse. Integration and differentiation are reverse. Okay. So integration of this dp is p, one side, okay, left side. And here you write just constant terms, 6 minus 6 mu q divided by pi h naught q. And integration of 1 by r is what? Log r. I written log r. But here there is no boundary conditions. That's why I have to write C1. What is meant by C1? It is an integration constant. Integration constant. If this integration with help of boundary conditions 0 to 10, 0 to 1 like this, then there is no need of constant. But here integration won't have any boundary conditions. That's why I have to write integration constant one term. Clear? So that is p is equal to this constant value log r plus c1, that equation 4. But this equation 4 having an integration constant c1, that we have to remove that value. How you are going to remove that value or find out that value of c1? Yes, by applying the boundary condition. Any integration constant value means find out with the help of boundary conditions. In mathematics module 1, with the help of boundary conditions, you are going to find out the constant value of integration. Same thing here also. What are the boundary conditions? Boundary conditions there? Yes, pressure as well as radius. When the radius changes, pressure is also changes. Same thing I used here. To eliminate C1, then apply the boundary conditions. First boundary condition, when the pressure is 0. When the pressure is 0 or minimum? Minimum is 0. When r is equal to maximum means outside r naught. When r is equal to r naught and the outside radius, pressure is 0 or atmospheric pressure. First boundary condition. This is the first boundary condition. Okay. And use this value in the equation 4 and find out the value of c. So c1 is become, or c is become, okay, this value is 0. Okay. R in terms of r naught. R naught, when r is equal to r naught, p is 0, so 0, and here c1 as usual. And here minus is there. Once you shift to the right side, it is become plus. So plus c1 is equal to 6 mu q pi h naught cube log r naught. Now substitute this c value in the equation 4. I am substituting the value in the equation 4. So P is equal to minus 6 mu u cube by pi h naught cube log r. So log base e antandre we can call it as a ln. Correct? Either you can write as a ln or log base e. Okay. So r, and here c value is this one. Okay. And here you just take the common outside. What are the common values? I will take common outside. Okay. So if you take the common outside, then remaining is minus log r plus log r naught e. Okay. So ಇದು ಯಾವ ತರ ಇದೆ? log a plus log b. So ಏನಾಗುತ್ತೆ ಅವಾಗ? When log a minus log b means you can write it as a log a by b. Okay. When log a plus log b means log a into b. ಗೊತ್ತಿದೆಯಲ್ಲ mathematics equation, same thing I am used here. So it is become a log r naught plus ಇರೋದು ಮೇಲೆ ಬರುತ್ತೆ, minus ಇರೋದು ನೆಗೆಟಿವ್ ಕೆಳಗೆ ಬರುತ್ತೆ. Okay. So log r naught by r. This is what the pressure distribution or supply pressure. Okay. This is the supply pressure of this hydrostatic bearing. And here I want inlet pressure. If I want, that is pressure. Okay. Pressure of pressure of imaginary element. Pressure of imaginary element. Now I want inlet pressure. Okay, ಏನಾಗುತ್ತೆ? If I want inlet pressure means R is replaced by Ri. R is replaced by Ri. ಇನ್ನೂ ಅರ್ಥ ಆಗಲಿಲ್ವಾ? Here R ಅಂದ್ರೆ it is a radius of imaginary element. Okay. So Ri andre inlet pressure, R naught andre outlet pressure. Okay. So here, so this pressure is pressure of imaginary element because it is in terms of R. Okay. If I want pressure, inlet pressure means I have to replace P by Pi inlet pressure and R by R. So now the equation will become same thing, 6 mu q by pi h naught cube ln R naught by Ri. That is the pressure of inlet pressure. It is in terms of inlet radius, outlet radius. Clear? Here I want flow means flow Q in terms of Pi or in terms of R naught and Ri. I just separate this term. The term na separate ಮಾಡಿ and all the values are shifted to left side. So Q will become pi. It is in the denominator. Now it is become a numerator. Okay. Pi h naught cube Pi by 6 mu log or ln R naught by Ri. So this equation 6 we can call it as a flow rate for hydrostatic lubrication. This you can see in the data. The hydrostatic. See, this is the equation. This is the previous equation. Okay, pressure ratio, and this is the ratio of flow. Q is equal to, just compare the equation. Correct idea? Nodri. Okay, same equation. We derived flow rate. So next, yes, a load carrying capacity of hydrostatic bearing means a load. W is the radial load. So what is its capacity? So in case of hydrodynamic, only one part is there. But here, the load carrying capacity having in two parts. You can observe the equation. This equation, W, you can get in the data handle. So in the data handbook, that equation is also available. See here. In this data handbook, you will get load carrying capacity equation. You just take this equation and substitute the values and integrate. Okay, the same equation I used from the data handbook. If you want, you can write it from the data handbook. W is equal to pi Ri square Pi plus integration Ri to the R naught P 2 pi R into dr. Okay, this part consists of two parts, this load carrying capacity. One part is, of course, from the outside pressure. This is from the outside pressure or supply pressure. Correct? Outside from the pump, we are supplying the pressure. That is also contributing to the load carrying capacity. Similarly, this part is, it is also load carrying capacity. It is because of a dynamic action of the fluid. So in the fluid only, it will generate the some pressure. Because it is rotating, shaft is rotating. Because of that rotation, it will generate the some pressure. That pressure is also contributing to the load carrying capacity. So here two types of pressure. One is supply pressure, which is from the outside, plus inside generating pressure. The two pressures will contributing to the load carrying capacity of hydrostatic bearing. Clear? So now we already know that P means it's the pressure of imaginary element. That is what we derived 6 mu cube by H naught cube log R naught by R. Derive ಮಾಡಿದ್ವಲ್ಲ ಇದನ್ನ just only previous. Okay, same equation. ನಿಮಗೆ ನೆನಪಿಲ್ಲ ಅಂದ್ರೆ you can get it from the data handbook. And substituting this value into the above equation 1, I am substituting that value into the above equation. P ಇದೆಲ್ಲ ಆ P value ಗೆ I am going to substitute this P value. Okay, the P value in above equation. Now it is become, okay, and here you simplify. So you can get cancel the common terms. 5 is get cancelled. Okay, 2 into 6, it is become 12. Okay, mu q H naught cube and Ri to the R naught log R naught by R into R into dr. Okay, so these terms are eligible to integrate, and these are the common terms I took outside. Clear? I took outside common terms, and these terms are can apply integration. But it is possible to integrate equation 3. Is it possible to integrate? Because log R naught by R is there, R into dr is there. Yes, it is in terms of ಯಾವ method ಇದೆ integration. Go back to the M1 M2. It is in the product method, UE method. ನೆನಪಿದೆಯಾ? By parts method, integration by parts method. Yes, it is in terms of integration by parts method. See, this is the constant terms I written as it is. Okay, only this is a integratable, and here log R naught by R we can call it as a U. Okay, and R into dr we can call it as a dV. U into dV. Okay, it's a parts method. That parts equation is integration U dV, which is equal to UV minus integration of V into du. Correct? This is a integration by parts method. You already know this equation. So this equation I am going to compare with here. So I make this as a U term, this as a dV term. I write here. ನೋಡಿ ಇಲ್ಲಿ dV ಅಂತಂದ್ರೆ R into dr. U means log R naught by R. So ಇಲ್ಲಿ ಏನೇನು ಬೇಕು ನನಗೆ U V ಬೇಕು and du ಬೇಕು. So ಇಲ್ಲಿ dV ಅಲ್ಲಿ V ಬೇಕು ಅಂದ್ರೆ we have to apply integration. So it is become a V. V is equal to R square by 2. ಅಂದ್ರೆ apply integration. If you apply integration to the dV, it become V. And here U ಇದೆ. ನನಗೆ du ಬೇಕಂದ್ರೆ differentiation. So du is equal to minus 1 by R into dr. Clear? So these are the values I know here. I make separate. So u ಅಂತಂದ್ರೆ already ನನಗೆ ಗೊತ್ತಿದೆ. U means log R naught by R. into V ಅಂತಂದ್ರೆ r square by 2 minus integration V ಅಂತಂದ್ರೆ r square by 2 minus du ಅಂತಂದ್ರೆ minus 1 by r dr. So here r get cancel ಆಗುತ್ತೆ. here one r is there, another r is there, get cancel. So finally ಏನು ಬರುತ್ತೆ ನಮಗೆ, so this is a okay term already integrated, but here this term you have to again integrate ಮಾಡಬೇಕು ತಾನೆ ಇದಕ್ಕೆ. So log r naught by r square by 2 same thing, and here for this ಏನು ಉಳಿಯುತ್ತಲ್ಲ ನಮಗೆ r by 2 into dr ಉಳಿಯುತ್ತೆ. ಅದಕ್ಕೆ ಇಂಟಿಗ್ರೇಷನ್ ಮಾಡಿದ್ರೆ ಏನಾಗುತ್ತೆ, r square by 2 into 2 4, 2 ಇದೆ ಇಲ್ಲಿ ಸ್ಕ್ವೇರ್ ಮತ್ತೆ 2 ಬರುತ್ತಾನೆ, so it is 4. So r square by 4. Now apply the limits ri to the r. So same thing, if you substitute r naught, the whole term get cancelled. Log 1 means 0. Okay, only remains r naught square by 4. Next I have to apply ri. So if I substitute ri, log r naught by ri square by 2 minus ri square by 4. So ಎರಡು ವ್ಯಾಲ್ಯೂ ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡಬೇಕು ತಾನೆ ಇಲ್ಲಿ ಇಂಟಿಗ್ರೇಷನ್ ಆದಮೇಲೆ. ಸೊ ಒನ್ ವ್ಯಾಲ್ಯೂ ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡಿ ಮೈನಸ್ ಆಫ್ ದಿಸ್. ಮ್ಯಾಥಮೆಟಿಕ್ಸ್, ಸಿಂಪಲ್ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ನೀವೇನು ಮಾಡಿದಿಲ್ಲ M4 M3 ಅದೇ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಯೂಸ್ ಮಾಡ್ತಾರೆ ಇಲ್ಲಿ. 5 minutes ಇದಾಗುತ್ತೆ, ಫಿನಿಶ್ ಆಫ್. So 1 by 4, take the common outside, entire thing just take the common outside. 1 by 4 is common, r naught square minus ri square minus ri square by 2 log r naught by ri. We can rewrite. And here and this value ಇಲ್ಲಿ ಏನು ಬಂದಿತ್ತಲ್ಲ ಈ ವ್ಯಾಲ್ಯೂನ ಇಲ್ಲಿ ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡ್ಬೇಕು ತಾನೆ ಬೇಕಾಗಿರೋದು. ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ದಿಸ್ ವ್ಯಾಲ್ಯೂ, ಯಾಕಂದರೆ ಇದ್ರದ್ದು ನಾವು ಇಂಟಿಗ್ರೇಷನ್ ಮಾಡಿರೋದು ಈಗ. We did integration of this part. Just substitute here in the equation 3. Okay, and after simplifying, substituting and after simplifying and cancel the common terms, we'll get final equation. W is equal to 5 pi r naught square ri square by 2 log r naught by ri. This equation 7 we can call it as a load carrying capacity of this equation 7 is an load carrying capacity of hydrostatic thrust bearing. Hydrostatic thrust or step, whatever it may be, step or thrust bearing, this W. You get the same equation here, the data angle. Load carrying capacity, okay, here W is equal. The same equation we derive. Is it clear?